is Anastasia Shlentsova, and she will talk about X-ray properties of the most luminous quasars with strong outflows.
So, yes, thank you for having me here today. Oh, not supposed to happen. I'm presenting to, my name is Anastasia Shlentsova, yeah, quite hard to pronounce, sorry. And today I'm presenting the work that I'm doing, I did as a part of my PhD thesis together at the University of Florence and Pontificia Universitat Cattolica about X-ray properties that we observe for the most luminous quasars with a strong outflows. So that was probably discussed widely last week, that AGN-driven outflows are a promising mechanism to explain coevolution. And we see predictions of those outflows from theoretical models, from numerical simulations, with the evidence of outflows in UV spectra, in broad absorption lines of about 20% of quasars. UFOs that were mentioned today as well, 30–40% of quasars have them in X-ray, but we still lack a complete understanding about all the interconnections between UV, X-ray, and outflows. And a couple words about what will be called in my talk a normal quasar. So in 2020, Lewis et al. Presented a sample of clean objects for which we can measure the more or less intrinsic UV and X-ray luminosities. And they show that for those quasars, the relation between UV and X-ray that can be accessed nonlinear relation that is also usually referenced as alpha X parameter. It has a tight dispersion of tighter, usually referenced, of about 0.2. So the dispersion is not intrinsic in what we observe. But then to further understand where this dispersion comes from, we need to understand where the weakness is coming from. And in Hitchhiker's Guide to the AGN by Murray et al., they proposed need for a soft X-ray observer here in the light gray area that would shield the broad absorption line region from overionization, allowing for light driving. And for example, in bulk quasars from SDSS DL5, it is indeed observed in agreement with the model that for C4 velocities measured as the highest and lowest blue shift of the caveat, higher outflows correspond to a high difference between measured and predicted by the relation alpha X. And then in the series of papers studying a sample of 30 quasars at redshift about 3, Lusso, Trifaloni, and others found the high fraction of X-ray weak objects and came up with this sketch. There is a lot of things going on. I reference you to a Trifaloni's paper to see all the details, but what is important for my talk today is that in the case when we have disk wind, the inner accretion disk gets depleted. So the corona, compared with the normal ones, starving, and therefore X-ray weakness can be explained without soft X-ray observer. And further evidence, apart from the sample that they used, comes from Timlin's work, who found marginal, but still a correlation between C4 blue shifts and the difference between observed and predicted alpha X. And further evidence comes from Zappacosta's observations of highly luminous quasars that were de-extincted. And here The red circles show X-ray weak objects, and they claim to see the correlation between C4 velocity and X-ray weak. So the state art of the problem is we do see quasars with broad absorption line features to be preferentially X-ray weak, but it's hard to disentangle if this X-ray weakness is intrinsic or due to absorption along the line of sight. And then for samples with a high fraction of X-ray weak sources, we see them having outflows. But it's kind of biased point of view on this relation. So our aim was to unbias all these things. And we decided to do a blind X-ray analysis of UV selected sources. We started from the SDSS DR16 quasar catalog in the range from 1.8 to 2.2 redshift. And you can see on the plot of CFOS and redshift versus UV luminosity at 2500 angstrom, that at higher luminosities, fast outflows are more common. In this area, the distribution of sources is more or less symmetric, and then we see more sources here. So as a preliminary selection, we took those sources in the corner, having outflows measured by Wu and Chen higher than 1400 kilometers per second, then luminosities logarithm of luminosity more than 46.8. And then since this selection is based on automatic simple fit, we investigated each source individually. There are many different ways to measure C4 outflow velocity. In Wu and Chen catalog, they are measuring the difference between rest frame C4 wavelengths shown here as a dashed line, and the centroid wavelengths, which divides the line into two parts with same flux. And we instead fitted the C4 range of the spectra and measured the outflow velocity as a difference. So we modeled it with multiple components and measured the outflow as a difference between the, not sure if you see it very well here, but the broadline region component shown in brownish color, and the additional blue shifted component for the outflow shown in orange. So the difference between these two blue errors. Here is a couple of more examples to give you some understanding of objects in our sample. And in this individual investigation of the spectra, we also removed all radial out sources. We removed broad absorption line quasars, confirmed the presence of blue shifted component, and ended up with a sample of 10 objects. One was observed some time ago. The other 9 we proposed for Chandra observations. The last one that is not filled will be observed next week. At least it's scheduled to be observed next week. So if you're around, you can approach me and ask what we measured there. And here is the fitting of our Chandra observations. So you see the typical spectrum that we obtain. It's not good enough to have a detailed spectral analysis, but it's still sufficient to accurately estimate flux. And initially, we adopted a model of power law corrected for galactic absorption and for local absorption in the vicinity of the object, but we don't see any excess absorption with 95% confidence. So final model that we used was just a power law corrected for galactic one. Here is another couple of spectra to show you a range of quality. Just look at that poor guy. We could probably name all the photons in there. Some were a little bit better, but it's still good enough for us. And finally, we supplemented our 10 quasar sample with some archival observations. We slightly changed our selection. We looked for quasars with centroid shift from Wuenshan being more than 3,000 kilometers per second, but we relaxed our luminosity criterion to be above just 46.3 and found 4 objects having available X-ray observations. 2 observed with Chandra, and there are references to publications where we put the X-ray properties from, and 2 more we found in serendipitous source catalog of XMM. For those 4 objects, we also measured C4 velocity in the way that I described before, to have all the C4 velocities measured uniformly in the same way. We firstly looked into photon index distribution. So X-ray weak quasars on average have a flatter X-ray spectra because absorption mostly affects soft X-ray, ending up in a smaller photon index. And in red, you see the distribution of photon indexes in a parent sample that was used to assemble the cosmological sample presented in LUSA in 2020. And they adopted a cut on the photon index of 1.7. So all the sources here were excluded from their sample. And you can see that out of 10, well, 9 in this case, 9 objects in our main Chandra sample, most of them reside at higher photon index region, just 2 are below the cut adopted in L20 sample, which indicates that they're probably not X-ray weak, more likely X-ray normal. And indeed, that's what we find. So here you see the same plot as at the beginning with L20 sample and the nonlinear UV to X-ray relation fitted to it. And then in yellow to blue color coding based on our C4 velocity measurements, some certain sources in our sample. And most of them are X-ray normal within the 3 sigma dispersion. This one was non-detected, and this one from Chandra sample, the poor guy with could be named photons, is X-ray weak, but if we assume it to be highly absorbed instead of weak, and if we fix the photon index to be an average photon index of 2, it jumps up and becomes X-ray normal too. And you could have noticed from, for example, the table I was showing that some sources have high errors on C4 measurements. For example, this one, the velocity could be anything from 2,000 kilometers per second up to 10,000 kilometers per second. So we decided to isolate those sources that have more reliable, let's say, measurements. And we divided our sample into objects that have securely high outflows above 4,000 kilometers per second or within 2 sigma range, and all others. both X-ray weak sources in our main overall sample fell into this extremely outflowing subsample. And then I put here 5 because source from next week is also fallen in here. And then we calculated the probability for this subsample of extremely outflowing ones and the others to have the same underlying fraction of normal to X-ray weak objects. And we find that the probability for them to have same fraction is about 23%. And even if the source from the next week is X-ray weak, the probability drops to be more than 10%. So it's still below 2 sigma confidence. Therefore, we don't see any significant evidence for the correlation between C4 velocity and X-ray weakness. And I think no, I still have something else to tell you before I run out of time. I mentioned before the LUSO 2020 sample. It was assembled for cosmological applications of quasars, and to actually use that sample in cosmology, we need a derivation of luminosity that we do from the nonlinear UV to X-ray relation to be independent of the cosmology model that is assumed. So in order to do that, we need to divide the sample into some samples in narrow redshift bins, therefore having the dispersion in derived distances smaller than intrinsic dispersion of the relation. In this case, we can use fluxes as a proxies of luminosities. And then additionally, looking in narrow redshift bins and evaluating the relation in them, we can see if we observe any evolution of the relation slope. So we compared our objects with what was evaluated for L20. In red lines, you see the slope that we get from L20 from the parts of L20 sample in the corresponding redshift bins. And then in blue is the slope that we get when we add our sources to that part of the L20 sample. And as you can see, within the errors, the slope doesn't change at all. And you can also notice that we don't observe any trend, any stable trend in the change of the slope of the UV to X-ray relation, which kind of verifies the absence of evolution. And yep, here's the summary. We did a blind X-ray analysis of certain extremely luminous radio-quiet non-bulk quasars, for which we confirmed strong outflows with our measurements. We find that the fraction of X-ray weak objects in the sample is in agreement with what is typically observed for quasar populations, and that the probability of X-ray weakness to be correlated with C4 outflow velocities doesn't show significant evidence to be present, which leads us to the conclusion that X-ray weakness is not directly correlated to the outflow velocities as it was thought before. At least it's not a clear necessary condition as was proposed by Murray et al. And we additionally checked the slope of the relation in narrow redshift bins and show further support for quasars to be used as standard candles. Thank you for listening to me, and I'm ready to answer your questions.
Anastasia. So Questions from the audience?
So, I mean, you and I can talk offline, but I mean, I think worth mentioning in public is, I mean, it does seem like we may need to redefine alpha X. I mean, the previous talk, I think, showed clearly the QSO SED models, 5,100 angstroms are all consistent, 1,350, they're very different. 2,500 is kind of in between. And so I guess the question to you would be, do you have a sense for, if you were overplot models, like how consistent are those 2,500 angstrom points? And if they're not consistent, then to actually compare LFOX between different sources, we might need to limit, subsamples first.
Well, I know that Guido's team was studying which wavelengths in UV and optical is the best one for alpha X, or we're using it not in the form of alpha X, but in the form of the relation itself. And although they tried some lines and some other wavelengths, they still come back to 2,500 angstrom as the most stable one for reducing the dispersion. So, I mean, the biggest problem for using quasars in cosmology is that we don't completely understand the accretion physics, as we discussed in the morning today. So if we understand the physics better, come up with a model that we will all agree, and then can derive explanation for the dispersion of the relation from the physics, then we can decide that, okay, this particular wavelength is the best one for our purposes. But at least for now, 2,500 angstrom is, let's say, cheapest one, because we have most amount of observations and the biggest sample, which is what we need for statistical evaluation of this relation.
Yes.
You take a look at their carbon-4 equivalent widths. I was wondering if your outflowing sources have any similarity to those quasars.
I didn't look into equivalent widths. It's something that we could probably do, yes. In this case, we just wanted to confirm that there is additional outflowing component that we need to explain C4 line shape.
Okay, go ahead, and then I have a question.
Just quick question. So we know at least for a subset of EAL quasars that they are intrinsically X-ray weak, and especially those that are a little bit more obscured. But there's a question of whether that's due to and other things. So how much of this could be due to orientation effects? Because your outflows here are detected in the mission versus the outflows that are in the quasars detected in absorption. How much of this X-ray weakness could just be because you're not looking directly through a large column density?
Well, thank you. That's a very important question, because indeed it could be that we have C4 as a kind of proxy of orientation, and that could be the reason for this inconsistency that we observe in different samples, that for some objects we just look through this dense region where lots of things happen in obscuration and blue shifting of C4. But I mean, it comes back to physics. If we can explain all the details in a consistent way, that would be very helpful. And for my cosmological application of quasars purposes, it would be also very useful if we can use C4 as an orientation measurement and have a subsample of a particular orientation. It would be nice to have it confirmed.
Probably this also answer a bit my question because I was asking, so you're finding results that are quite different, no correlation with respect to the one of Zappacosta et al. So the main difference is that in Zappacosta et al. Paper, okay,
Go back to Zappacosta's plot.
yes. Okay, so what are the properties of this sample? Are these bulk?
No, they're not bulbs, but they have a little bit higher luminosities. Their criterion was above in logarithm, but they have something that we call the reddening and the absorption. So as I understand, they were correcting for it in their X-ray modeling. Actually, in my sample, I have one of their quasars. I'm not sure which one exactly, but the point is that even for that one quasar that we used in our sample, we don't observe evidence for any absorption in excess for galactic one. So it's a question of how exactly they're evaluating alpha X there.
These are type one quasars?
I think, yeah, I will take
Okay.
this.
This is XMM Newton data. May have more counts to be able to make that correction.
Maybe, yeah.
Yeah, these are, I think it's archival, different archival.
It's a VSSH.
Which sample?
Yes, that's that one.
The parameter space in terms of velocity shift is the same that you were.
In the velocity shift is the same that I have, yes. So here it goes up to, here the C4 blue shift is reverted, so it's up to 4s, up to here. And indeed, even on the Pacosta sample, you don't see much of the correlation up to 3,000-4,000 kilometers. But then when we go to our plot of the same type here, we go up to 7,000 kilometers per second. And I mean, this
Yeah.
one is not making any sense with the
You don't have points here.
Yeah,
We're a bit populated in the other plot.
yes, but we wanted higher shifts initially. And anyway, in their plot, they don't have any correlation clearly observed in this part. But then for this part, they observe a correlation, and we don't.
Related on this, I don't see errors in the alpha X when there are big errors.
So that one is
I mean the error.
oh yeah, okay, yeah. Well, I did it this plot yesterday night. Sorry, didn't have time to.
To have an idea of how solid are these, I mean, going back to the question on the counts in the X-rays and how well you can constrain these quantities. I think that for the very low counts objects, you should have quite a big errors here.
That's
Yes.
cool. So I'm actually really curious about that large error bar. What causes it to have such a large, yeah, why is such large?
That's a very peculiar object. It has it's one, I think, and something is going on there in spectra. I didn't do the fitting of C4 range myself, but there was some problems with this one. There were also some questionable part with the last one from XMM because everything seemed to be blue shifted in there.
Okay.